This lecture continues the quantitative examples involving the conservation of energy, where we have, for example, gravitational potential energy transforming back and forth into kinetic energy. At the end of my last lecture, I went through a nice comprehensive example involving a roller coaster. There are two more similar situations to take a look at to follow. Once again, these have to do with roller coasters. Both of these problems are pretty similar to each other, and they are given in terms of mathematical symbols rather than numbers. That's perfectly fine. Okay, let's go ahead and take a look at the first of those two. As I said, these two examples are pretty similar. Okay, a roller coaster cart begins at rest at the top of a hill of height h on a frictionless track. The cart passes through a vertical upside-down loop with a radius of curvature capital R immediately after the hill. What is the minimum safe height of the hill previously such that the cart safely makes it through the upside-down loop? Okay, so our situation is as follows. We have, first of all, a basic drawing like so. We're going to have my cart here like so, of mass m, initially begin at rest at the top of this hill h. This hill h here is our unknown. Okay, now qualitatively, first of all, the following happens. We start here with all gravitational potential energy, which then gets transformed into kinetic energy as we move towards the bottom here of the diagram. Incidentally, it does say in the problem that this is a frictionless track, so then therefore the energy is conserved. Let's note that here. Okay, and then we have all kinetic energy here at the bottom, which then subsequently transforms partially into potential energy as we move up through the loop. So as we begin to move up through the loop, we slow down, and then therefore we reach our slowest speed here at the top of the upside down loop like so. We'll have some speed v. Okay, and then subsequently we begin to move downwards once again. So then therefore some of the potential energy transforms back into kinetic energy as we move downwards. This then means that the speed increases as we move downwards. But as we move through the upside down loop, we will have the slowest speed at the top of the loop. Okay, now let's keep the geometry here simple. It does say in the problem that right here the radius of curvature is capital R associated with a circle. Let's just assume that this vertical upside down loop represents the diameter of such a circle. So let's consider this height here, just to keep things simple in terms of the geometry, as 2r. Okay, now because the energy is conserved, let's just begin by writing out our conservation of energy equation and see what it tells us. So we have 0 equals delta k plus delta u, and then we just have to fill in all of our terms. So right here, first of all, is our final kinetic energy with this unknown speed v, and by the way, this speed v, as it does say in the problem, is the minimum safe speed to safely make it through the upside down loop. So this is the minimum safe speed. Let's note that. But now continuing to fill out our expression, we're going to have that final kinetic energy, 1/2 mv squared, and then minus the initial kinetic energy here of 0 because we begin at the top of that hill at rest. Okay, and then we have changes in gravitational potential energy. Well, we'll consider here the bottom of the diagram as height 0. This then means that right here we will have a final potential energy with this height of 2r. So the final potential energy is going to be mg multiplied by that height. And then minus the initial potential energy up here, which is equal to mgh, where h is our unknown, like so. Okay, and now with this expression, we have, thus far, one equation and two unknowns. The two unknowns are the minimum safe speed v to safely make it through the upside down loop, and the h that we're trying to find. So what do we do from here? Well, we can actually calculate what the minimum safe speed is by going back, for example, into our unit on centripetal force. So now let's take a look at the forces acting on the roller coaster cart at the top of the upside down loop. Okay, so here's the top of the upside down loop, and then right here's the coaster cart like so of mass m. It does say it's a frictionless track, so then therefore tangential to the circle, no forces are acting upon the cart. However, in the radial direction, we do have the following. From its own inertia, the cart pushes against the track like so. Think of that in terms of the centrifugal force from the non-inertial reference frame. Therefore, however, from Newton's third law, the track pushes back. So in other words, right here in this direction like so, we have the normal force. And then of course, in addition to that, we have the cart's weight, straight downwards, mg, Both of these forces here in the radial direction point in the same direction as the centripetal acceleration vector, a sub c, which is inwards towards the center of the circle, which is down here in the diagram like so. And now let's just add the forces using F equals ma. So I've got two forces here in the same direction as the acceleration, so they're both positive, and then I set that equal to the net force mv squared over r, where r, by the way, is capital R. It's the radius of curvature here of the track at this position. Okay, now what do we do from here? Well, imagine taking the speed v and making it smaller and smaller. If you do, this then means that the right-hand side of the expression gets smaller and smaller. In order for that to happen, however, the left-hand side of the expression has to get smaller and smaller as well. But the weight of the cart mg is a constant. Therefore, the only way for the left-hand side of the expression to get smaller is for the normal force to get smaller. Eventually, at the minimum safe speed to safely make it through the upside-down loop, the normal force will go to 0. Now, I can demonstrate that for us here, by the way, by using this coffee can. You saw this demonstration at the beginning of our unit on dynamics, and I said at the time that we could actually calculate the minimum speed necessary for the water to safely make it through the upside-down loop. That's essentially what we're doing here in this problem. Now let me go ahead and twirl this into a vertical circle like so. And now what I'm going to do is I'm going to slow the can down, and as I do, the tension decreases. Eventually, at the minimum safe speed at the top of the upside-down loop, the tension force will go to 0, like so. And when that happens, then the water inside the can, for example, would become a projectile. Same thing happens here. So what we're going to do is we're going to calculate the minimum safe speed v such that the normal force goes to 0. This all occurs as an instant in time, so think of this as taking a limit. So we take a limit as the normal force goes to 0, and then therefore when we do, the expression becomes the following. And now what I'm actually going to do here algebraically is I'm not going to solve for the speed v. Instead, what I'm going to do is I'm going to solve for the quantity mv squared. And the reason I'm going to do that is because it actually appears up here, like so, in my conservation of energy expression. So this will make the math a little bit easier for us to do. So let's move the capital R here to the other side, like so. And now I'll take that expression for mv squared, and then we'll jump up to the top board and plug that into our conservation of energy expression. Let's see what happens as we do. Okay, so I have now, first of all, 0 equals then 1/2 mv squared, so 1/2 mgr, like so, from the bottom board, and then plus 2 mgr, and then minus mgh. And now what we do is we solve for h. So move this term to the other side, so I get mgh, like so, equals, and then add these two terms together. Notice it's 2.5 or 5/2 mgr, like so. And then the weight of the coaster cart, mg, cancels from the expression, here and here. And then therefore the answer is as follows. The minimum safe height of that preceding hill, such that you could subsequently make it through the upside-down loop, has to be at least 2.5 times the radius of curvature here of the upside-down loop at this position. This is assuming, of course, that we're considering the diameter here of this upside-down loop to be equal to twice the radius, just for simplicity. Now, in a realistic situation, there are a couple of things that are different here in an actual roller coaster situation. For example, usually at the top of this preceding hill, the coaster cart already is moving a little bit, and it then therefore has some kinetic energy. If you already have some kinetic energy, that will then allow you to lower, if necessary, the height of this preceding hill, such that you can still safely make it through the upside-down loop. In addition to that, particularly with older roller coaster designs, you're going to see the upside-down loops shaped not as perfect circles, or nearly as perfect circles, but instead as ovals, like so. Something, for example, that, say, looks like this. This is particularly pretty common in some really old roller coaster designs. A nice example at Magic Mountain of an old roller coaster that has this incorporated into its design is the ride Viper. Now, in this particular situation, take a look at how tight the turn is here at the top of the upside-down loop. If I draw here an imaginary circle associated with that portion of the turn, notice that the radius of curvature there is really small. Basically, the smaller the radius of curvature, even at a relatively slow speed, The smaller the radius of curvature, the bigger this number is. The bigger this number is, then the normal force will not necessarily be equal to 0, such that you could safely make it through the upside down loop without the need of restraints. Now, of course, that's impossible in an actual physical situation involving roller coasters. Roller coaster trains do not leave the station until everything has been locked in place as it should be. But with respect to Viper at Magic Mountain, it's actually a pretty poorly designed ride. You may have noticed, for those of you that have ridden the ride, that it's actually really rough. It throws you around a lot, and that's because it dates back to a time before the use of computers that are used in engineering today. In addition to that, as tall as the initial hill is on that ride, it's really not tall enough, because by the time you reach the end of the ride and you go through the last couple of corkscrews at the end of that ride, it's like you're sagging in your restraints as you move through the tops of those ups and down loops, because at that point the coaster train is actually moving pretty slowly. So as impressive as that ride is, quite frankly, the initial hill is not tall enough. They should have made it even taller than it is. Okay, now that's the first of our two examples here. Let's take a look at the second of these two examples. It's pretty similar to the example that we just did here. Okay, let me go ahead and do some erasing. Okay, I'll move my file here in just a moment. I'm going to keep a portion of the diagram, however, because it also carries over into our next example. Okay, let me move my file. Okay, let's go ahead and take a look at the problem. Okay, a roller coaster cart begins at rest at the top of a hill of height h on a frictionless track. The cart crests a second hill with radius of curvature capital R immediately after the first hill. That looks like this. Okay, so here's this subsequent second hill like so. Here's our coaster of mass m with a speed v. What is the maximum safe height of the hill of height h, such that you can safely make it over this subsequent hill without becoming projectile? In other words, if you go quickly enough over this second hill, you will in fact leave the track and become projectile. So then therefore this speed here is going to be a maximum safe speed. Okay, now we're going to once again keep the geometry here as simple as possible. Let's assume, for example, if this right here is an imaginary circle associated with the top of this hill, right here is its radius of curvature. Let's assume, for example, that the diameter of this circle is the same as 2r. Just to keep things simple, this right here is the height of that hill. Once again, we're making this as a simplistic approximation, much like I did in the previous problem involving the upside down loop. Okay, now, mathematically, this problem is almost identical to the example that we just did a few minutes ago. What we're going to do is calculate the maximum safe height of this hill, such that you can safely make it over this subsequent hill. Let's go ahead, first of all, and set up our conservation of energy expression. It's identical to what we did in the last example. Okay, so 0 equals delta k plus delta u. Let's go ahead and fill in our terms. So we're going to have here a final kinetic energy with this maximum safe speed, which is unknown at this point. We're going to have to find it in just a few minutes. So 1/2 mv squared, minus then the initial kinetic energy up here, which is 0. Okay, and then change in gravitational potential energy. We'll have a final gravitational potential energy here of mg multiplied by the height of 2r. And then minus the initial potential energy up here, which is mgh, where h's are unknown. So as I said, this expression here is identical to the conservation of energy expression that we saw in the previous example. But once again, there are two unknowns here. The height h that we're trying to find, and right here, the maximum safe speed v. But we can once again go back to our unit on dynamics involving centripetal force to find that maximum safe speed. Here's how we do that. Okay, so let's say that right here is the top of the second hill. Here's our coaster like so of mass m, and then right here is this maximum safe speed. It's once again a frictionless track, so no forces are acting on the coaster cart tangential to the circle. But of course we do have forces acting in the radial direction. In the radial direction, we have the normal force upwards like so acting upon the cart, and then right here is the weight mg downwards. But these forces don't cancel because we do have a centripetal acceleration like so, inwards towards the center of the circle, which is down here. And now we add up the forces using F equals ma. mg will be positive in the same direction as A, and the normal force in the opposite direction will be negative. So when I add up the forces, I get mg minus n is equal to ma mv squared over r. And now here's how we analyze this force equation. Now what we want to do is make the v here, for example, larger and larger. So what we're trying to calculate, once again, is the maximum safe speed. So if I make this number larger and larger, this number gets larger and larger, which then means that the left-hand side of the expression has to get larger and larger. But the weight of the coaster cart mg is a constant. So then therefore, in order for the entire left-hand side of the equation to get larger, what must be happening to the normal force? It has to be getting smaller and smaller. Eventually, if you go over that hill quickly enough, then the normal force goes to zero and you become a projectile. I've referred to this situation, by the way, qualitatively when describing roller coasters earlier at the beginning of our unit on dynamics. There's a section of the ride Goliath, for example, at Magic Mountain, where you go over a short, sharp hill like so. For just a moment, when you reach the top of that hill, you feel yourself rise out of your seat a little bit. Basically, the ride is engineered perfectly in this manner, such that this situation is happening. So once again, we let the normal force go to zero. And when we do, take a look at the force equation that we end up with here. It's mathematically identical to the force equation that we had earlier in the upside down loop problem. And then at this point, I do the exact same mathematical steps as I did in that previous example. I solve this equation not for the speed v, but instead for mv squared. So let's cross multiply the r to the other side like so. And then we take this expression for mv squared and then we plug it in up here into our conservation of energy equation. Let me write this out one more step. So going up to the top board, we have 0 equals 1/2 mv squared, so 1/2 mgr, plus 2 mgr, and then minus mgh. If you solve for h, you end up with the exact same thing as we did in the upside down loop problem a few minutes ago. You get that h is equal to 5/2 r. But in this case, the meaning of this number is different. This is the maximum safe height of this hill here, such that you could safely make it over this hill. If you make this hill taller than this value, then you would need restraints, for example, upon yourselves and also upon the coaster cart itself in order to keep it safely on the track as you crest this hill. In reference to Goliath, the next time that you do ride the ride Goliath, pay close attention to what happens before you reach that hill that I've mentioned. There is actually a brake that is applied to the coaster cart a few seconds before that hill, such that you then crest that hill at basically this speed, the maximum safe speed, and then subsequently you feel yourself rise out of your seat a little bit and then come back down as you crest that hill. The ride is engineered perfectly for that situation. Okay, this concludes the basic examples involving conservation of energy with gravitational potential energy.